everyone. Welcome to our fireside discussion about DeepSeek. I'm Edwin Schmier, co-founder and COO of Rotational Labs, and I'll be your moderator for today's discussion. First, thank you for taking the time to join us. We still have participants joining the event, but we'd like to get started in the interest of time. And before I introduce our distinguished group of panelists and dive into our discussion, I'd like to set the context and mention a few important housekeeping items. Presumably, we're all familiar with DeepSeek, a foundation model lab based in China that exploded onto the AI scene a little over 2 weeks ago, mostly because they claim to have trained an advanced reasoning model for less than $6 million. Now, if you've read their R1 paper, which we've all done, they heavily caveat that claim. And I want to be clear that we are not here to dispute that number. Still, it caught the attention of the world, especially because they open sourced their models and techniques. Regardless, if you believe their claim, which some estimate is roughly 30 times more efficient than what the other leading foundation model labs have been able to accomplish, it's placed a renewed interest on efficiency and cost. Now, to be clear, the consequences of that claim have been significant. We've all seen the share price of NVIDIA fall. There have been controversies about data generation. There have been geopolitical consequences. Meta has set up a war room. Sam Altman came out and said, well, maybe OpenAI should be a little bit more open. There is no lack of strong opinions about DeepSeek. And again, we are not here to talk about any of that. So please put all of that aside for the time being. And what caught our attention as a group of machine learning engineers are the optimizations and the techniques that the DeepSeek team has to a degree pioneered, shared, and open sourced. And we'll focus strictly on those techniques. And I like to use the analogy of a fireside chat, right? So we are a community of learners. There's a topic of great interest to us all. We've invited a group of distinguished subject matter experts to share their perspectives in a cordial manner. And my request of all of you is to, number one, keep that cozy fireside chat visual in mind as we go. And please, let's maintain our focus on the engineering optimizations. Okay, so before we get into that, a few housekeeping items to take care of. First, the usual disclaimer that the panel's opinions are strictly their own and do not necessarily represent their employers or affiliated organizations. Secondly, materials. You will all receive a link to the recording. We are recording this discussion. We also have an extensive reading list if you'd like to take a deeper dive. We will send that to you. Thirdly, we welcome questions. Please post your questions in the chat. We will try to get to as many as we possibly can. If we can't, we'll try to follow up afterwards. And lastly, a few public service announcements. Our next event is on Friday, February 28th, where one of our engineers, Patrick Desiel, will host a tutorial called Train Your Own LLM. It's a highly applied hands-on keyboard tutorial that's highly accessible to all participants. I've been through it. It's really cool. So please join us if you can. And then lastly, our team has a few publications coming out shortly. Specifically, Prima and Patrick, two of our machine learning engineers, have a book called Real-Time Machine Learning coming out in the next few months by Manning Press, though it is available for early release. And then Dr. Rebecca Bilbrow has Apache Hudi, the definitive guide, coming out with her co-authors later this year, which will be an O'Reilly publication. So with that, we can move on to introductions. Oops. First, we have Dr. Rebecca Bilbrow, co-founder and CTO of Rotational Labs. She's co-author of Applied Text Analysis with Python and founder of Yellowbrick, an open source machine learning library. Rebecca, you want to say a quick hello to everybody?
Welcome, everyone. Excited to be here with you.
And next we have Ilya Reznik, technical advisor and career coach at Instructed Machines. He's a friend of rotational and an experienced machine learning engineer in his own right, having had roles at Adobe, Meta, Twitter, Department of Labor, among others. So Ilya, you say a brief hello?
Yeah, hi. If you used the internet today, you probably used the model that I've trained, but I don't know how the mute unmute thing works. So sorry if there are any technical difficulties there. Nice to see everybody.
The basics. Yes, thank you for joining us. And last but not least, we have Steve Veldman, machine learning engineer at Rotational Labs, who recently joined us a little over a month ago, and he has over 10 years of experience in the manufacturing sector. Steve, brief hello.
Hey everybody, I'm excited to be joining my inaugural rotational webinar today.
Very cool. First, when we talk about DeepSeek, I just wanted to point out that, again, you might have different ideas in your head about what DeepSeek is. You could be thinking about the app. You could be thinking about the models. What we did here is we just wanted to paint a brief picture about the chronology behind what DeepSeek has released over time. So even though I said earlier that they exploded onto the scene, they've been around for quite some time, for at least the last 2 years, publishing about their optimizations and engineering techniques. And we're going to be throwing a lot of model names around, and this just kind of gives you, hopefully, a roadmap to understand what those different model names are, so that you have that in your head. And I'll probably go back to that slide just to make sure everyone feels oriented. So first, I'd like to start off with a question to Rebecca. So Rebecca, these are graphics that showed up in the V2 paper back in May of 2024. So as a machine learning engineer, when you look at this, when you see this, what stands out? What is interesting to you? What do you want to know more about?
Thank you for that question. I think that, maybe on sort of like a humorous level, I feel like one of the first thoughts I had is they sort of missed an opportunity to name their paper something like optimizations are all you need, because that's sort of a convention in our discipline to sort of suggest that all you need is just this one great trick. But I think that is sort of the story that these images tell. I would sort of, maybe I'll sort of speak at a high level, and I know that Ilya and Steve will also weigh in here, but I would say I would recommend sort of reading these charts starting on the right-hand side.
Okay.
So like this right-hand side is sort of about addressing some of the persistent pain points in machine learning, like training is expensive. And deployment is hard. And deployment is hard because it's hard, like even if you've managed to do training and you've got the model hosted, throughput is a problem. So I think, the story here is that some of these pain points have been addressed through some combinations of creative optimizations. And then on the left-hand side, the image, I think, sort of suggests that these optimizations don't cost you much in terms of performance. Mm-hmm. So at a high level, I think that's sort of what my quick takeaway was the very first time I saw these images. I thought optimizations are all you need.
Great soundbite. How about you, Ilya? Anything stand out for you?
Yeah, I mean, I think that star over on the left side really kind of tells a big story. And it reminds me of the early days of deep learning, where you would go to every conference and it's like, we trained like 2 hidden layers. And then the next year it would be like, we trained 10 hidden layers. And then the next year it's like, we trained 100. And then the next year it was like, we trained 5. And it's actually like really sobering to be in that place again, where we're like, no longer talking about like, well, if we can burn all the compute in the world, what can we do? Okay, but like realistically, we can't, right? And I think Rebecca was very right on the optimizations. The KV cache one really jumps out at me because whenever you do any training on these really big models, you're always memory constrained, and like that is like hitting you where it hurts, right? Like that, like what is it, 93% or something like that? That's huge optimization right in the place where it usually hurts. And it's nice to be having these conversations instead of like, where are we going to find another internet to throw at our problems,
Great points. How about you, Steve? Anything you'd like to add?
Yeah, so there's that star that Ilya referenced was like the first thing that grabbed my attention because normally we associate more parameters with better performance and also more parameters with, more costly training and more costly inference. And so that is that bodes well, I think, for the future of our industry as a whole, that we're trending sort of in that direction. On the right-hand side, two things really jumped out at me. I appreciate that this particular graphic is sort of, there's been a lot of to-do about comparing DeepSeek to other companies' models, and here we actually track their own evolution, the performance of their multiple or their iterative generations of models, which I think is a little more relevant. It's a little less of an apples to oranges sort of thing, so you can sort of see what they've done internally to sort of improve their process. Ilya mentioned the KV cache, so I assume at some point we're going to field a question about multi-head latent attention, and that is super important there. And at a very, very high level, that KV cache is like a very it's a big bottleneck. So it's time intensive to move that piece of information from one part of the GPU to the other, and making it smaller really is an important optimization that makes that important important enough to be one of 3 graphics on the right hand side of a flagship chart in their paper. So but that was
those are great points, and you're kind of getting ahead of me here, Steve, because I was going to the next question was going to be, in this V2 paper, what were some of the more exciting optimizations or things that were interesting to you that our audience should be aware of?
Yeah, so without getting like too deep into the minutia, this concept of the multi-head latent attention. There's a lot of different ways I think you can scramble those words around, and they mean mostly the same thing. But so multi-head self-attention is this cornerstone of transformer architecture that allows a model to sort of learn context and how words relate to one another. It's also really computationally expensive to do. And one of the great optimizations of the progressive generations of GPUs is that it's made all of the linear algebra behind that very efficient. It can move through that really, really quickly. But as the matrices that we're handling for this get bigger and bigger, there's other problems that are harder to deal with, and that's we kind of started already to talk about the KV cache. So that is in the traditional multi-head attention mechanism, that's about 2/3 of the vectors that are needed. And it's important to keep those at full resolution for the calculations the model does to be as effective as possible. But compressing them so they take up less space in memory when they're not being used, and so that they're easier and faster to move around to different parts of the GPU, is a really a big win, I think, for model efficiency.
Cool. How about you, Ilya? What optimizations excited you about this?
Yeah, I totally agree with Steve. And just to like add on to what he said, there's like an additional layer here. For the models this big, you're not even dealing with one GPU, right? And when you're doing distributed training against the cluster of GPUs, the cache in particular, like you've seen something, you put it on a cache on the one GPU, right? But like everything else hasn't seen it yet. And so like optimization there, just like, it like I said, it hits where it hurts. I think that's a huge thing in here. And I'm sorry, I might mess up the papers. I don't remember which topic came from which paper. But token dropping is another thing that like really kind of stuck out to me because it used to be that we would like grab onto every token. And funnily enough, I was at NeurIPS, which is like a flagship academic conference in December, and there were a bunch of people talking about like some tokens are far more important than others. And obviously their research came out before then, but I'm happy again to be having those conversations of like not every token is created equal. Like, do we need to look at every token? And clearly the answer, no, we do not need to look at every token. And yeah, it's interesting for me to see whether this will merge back to the world that I'm a lot more familiar with, which is like, I don't want to say hand feature engineering, but like having like some biases going into training these models, rather than being, again, like a lot of what I'm saying today, I guess, is my excitement about the bitter pill of machine learning, right? Like there was a paper that came out a
Right.
few years back in 2017, I believe, uh, where it was like, well, as a researchers, we do like all we can, and at the end of the day, more data, more compute beats you every time. And like maybe, right? Maybe it doesn't anymore. Maybe we reach the plateau of that where like we do want to drop some tokens. We do want to optimize our caches. I know we're going to talk about reinforcement learning beyond this because that's huge here. But honestly, like GRPO is somebody who's done reinforcement learning in production, like GRPO is probably the biggest innovation here of what I've seen. And like, yeah, there are a lot of things put together quite nicely. A lot of them we've talked about before as a community, but like to see it actually work in practice is pretty remarkable to me.
Yeah, and Rebecca, I know you have a background and expertise in reinforcement learning, so I think it would be great if you could talk a little bit about what you see from your perspective, given what Ilya has mentioned.
Yeah, I mean, I think the reinforcement learning angle is an interesting one because, on some level, I think it comes across as sort of like the least mature insight or like least mature optimization of the ones that they tried. And I think that I mean, on one level, that definitely mirrors my own experience doing reinforcement learning. It's very experimental. It is, it's much less popular, kind of common usage. There's way fewer, for example, way fewer open source libraries for doing something like reinforcement learning. And the ones that do exist are really geared towards kind of like pretty artificial simulation type things, like creating a game, not really designed for sort of real world problems. So while I think I would caveat and say, I think that there's still a lot of work needed to show how to apply reinforcement learning to these kinds of problems, I think that it's really exciting that they tried something like this, with an intention of, kind of figuring out how to extend context windows, since that's another pain point. Like, is reinforcement learning sort of something that can be used, to help us with like maintaining kind of like more attention for longer? I think it's a fascinating question. I agree, GRPO is really interesting. It's interesting because it addresses some of the known problems with reinforcement learning, which is that it can get kind of crazy, right? You get sort of these like sometimes crazy hallucinations. And if anybody has sort of looked into reinforcement learning before outside of the natural language generation context, you'll see sort of these crazy things that reinforcement learning does, like building robots that have like way too many arms, and just, or like, people, when you see kind of the crazy images of people where they have, way too many fingers, like those kinds of things. So like, it's not very stable because of the sort of exploration component, right? Reinforcement learning is about balancing exploitation of kind of some reward or avoiding some penalty, with like balancing that with exploration of trying new things. And trying new things is a little bit dangerous. It can be chaotic. It can lead to hallucinations that are hard to understand or diagnose. But it's a really cool technique in machine learning that I think the community has sort of been sleeping on. And so I think it's pretty exciting that it's sort of in the public discourse again.
Yeah, it's interesting. If you read the V2 paper, at the back of it, there is a short paragraph about online reinforcement learning. And it says something to the effect of, we tried online reinforcement learning and offline reinforcement learning, and online worked really well. And then it was a very short paragraph. And then, to the effect they said, we're going to look into this more. And then, fast forward to the R1 paper, which came out in January or December, I should say. And there is a huge focus on reinforcement learning as kind of a differentiator for them. So, it's fair to say, to a degree, I think, that they spent a lot of time doing exactly what you said, which is really dive into reinforcement learning and how it could potentially optimize their models and provide greater efficiencies. So that's really interesting. Ilya?
Yeah, Edwin, and that's not unique to them, right? Like everybody in the
Yeah.
industry is looking at reinforcement learning as the next thing and has been for at least last year. Reinforcement learning, I'm very excited about. Again, I've done some of it in production. It has, just to caveat, it has been the next big thing in machine learning for the last 20, 30 years, and it's never taken off, right? So like, there are some of these ideas that have been in the ethos, and it would be exciting if they worked. We haven't quite seen them work again yet, but this might be building us toward that.
So I'd be curious, as a follow-up, why has it not taken off? What has been the blocker? I mean, Rebecca mentioned that there's a lack of libraries out there. What's holding everyone back?
I mean, I think a big part of it is the lack of open source, like easily available open source options. But even if you control for that and you think of like the ones that do exist, like RLlib is one of the ones, I think probably a lot of people have experimented with GIM, or maybe like the TensorFlow agents package. So that, there's a couple, maybe there's like 5.
Okay.
I would say that the real issue is that it's extraordinarily difficult to define a reward function.
Interesting.
And I know that that sounds trivial, but that actually is one of the hardest things to do. Also, like when you're doing reinforcement learning, you have to like define the battleground, right? So not just the reward function, like what is going to increase or decrease.
Okay.
But you also have to just like say, what is the environment? You have to define that environment, which means you need to account for, as many things as possible that would happen in a real environment, which is extremely difficult, especially with things where humans are involved and like interactions are involved and language is, like highly perplexed. These are things that are very difficult to encode in rules and heuristics. So defining kind of the policies, defining the action space, defining the reward or penalty is hard. So I think that that's a big part of the problem.
Let's stick with reinforcement learning for the time being. And I would like to connect it to this idea of data generation. One thing that we know through work that we've done with partners and customers is that data tends to be a blocker for a lot of AI projects. And as I mentioned, reinforcement learning shows up in a big way in the R1 paper. So does DeepSeek prove that you can use reinforcement learning to generate high quality synthetic data?
I mean, I would say no. I mean, if I have to just give one answer, I would say no. I don't think that they proved definitively that you can sort of just use reinforcement learning instead of creating like human labeled data.
Mm-hmm.
But, and they proved that. Actually, they proved what I just said because they attempted to just use reinforcement learning to generate synthetic data and it didn't work. So they had to do more creativity.
Right.
So it's not enough by itself. But if you need synthetic data and you've never explored reinforcement learning, probably this has your attention now.
Yeah, to piggyback on that a little bit, I think what they proved is that you can use reinforcement learning to reduce the amount of human labeled data you need dramatically.
Okay.
I mean, that's still a very expensive part of the process. But as Rebecca mentioned, a lot of the challenges around reinforcement learning still require some kind of human defined parameters and gateways. Like the academic literature that I've read around reinforcement learning has all been about like training an agent to play Atari games. So where you have sort of like a very neat walled garden of like, here are the rules, here are your incentives, and the agent can very quickly learn how those things sort of work together. You know, human language doesn't really work like that, and human reasoning doesn't really work like that.
Right.
So I think that's where the supervised fine tuning obviously stepped in, and we saw the big improvement between R1.0 and R1.
R1,
And
yeah.
so, but that's no less of a, I mean, it's like a less flashy headline, but it's no less of an important development, because that massive reduction in the amount of we'll call it human intervention is huge.
Yeah, and
Dave?
I think that's all absolutely right. I like what Rebecca was talking about in terms of like, you know, if you can define your environment, reinforcement learning is really useful to you. And that's why we see it, you know, show up in academic literature in Atari and chess, AlphaGo, right? Like those things,
Right.
they're hard, but un they're not unconstrained. You need constraints in order to rein reinforcement learning in a little bit. Uh, about the about the artificially generated data, synthetic data, uh, yeah, short answer, totally agree. No. Uh, a little bit longer answer is sometimes. And honestly, the differentiator there is how much do you as a system designer understand about the system? Like if you can cover every edge case, then actually like, yep, uh, synthetic data is terrific. The problem is that the reason we use machine learning in the first place is that we can't cover every edge case. And in those edges, you will see it fail. That's when
Okay.
it fails. But, you know, it depends on what you're training for. Like if you're training to read a document and give you a summary, I don't know. I think it's going to do pretty well at that.
Mhm.
But, you know, sometimes that's my answer.
So let's shift our focus more towards another technique that they use called mixture of experts. Now, I know mixture of experts is not a novel technique, but perhaps their implementation of it is. So, Steve, I'd love to start with you and kind of get your opinion about what the DeepSeek team did with regard to the mixture of experts architecture.
Yeah, I mean, and I think it's helpful to start by sort of defining what the mixture of experts architecture is. In
Okay.
we'll call it a traditional transformer architecture, every piece of information that you're predicting on sort of passes through the entirety of the architecture. And when you're dealing with a 200 billion parameter model, that's a lot of linear algebra that you're asking that you're asking your GPUs to do, or your
Right.
cluster probably of GPUs in some cases. And so mixture of experts breaks down into a really neat analogy, and maybe that's like the better way to start. So like if you're a decision maker at a company, and you pretend you whatever company you're in, you need to be able to answer a question on anything. Nothing is off bounds. It could be fine arts, it could be medicine, it could be law.
Right.
The good news is you have an unlimited number of advisors, maybe not unlimited, but you have several billion advisors. The downside is you're paying them all by the hour. So in a traditional structure, you actually consult every single expert in your sort of team of experts, and whether they sort of are qualified to, or whether their expertise is on that question or not, you're getting their input in the final decision. I've sort of overgeneralized a little bit, but that's sort of like what you could conceptualize a fully dense transformer architecture. Mixture of experts allows sub networks within the architecture to be trained specifically on set domains. As you mentioned, like they're not the first people to do it. They've arguably done it very successfully here. But Google had a notable large-scale implementation of this in 2021. It was about a 1.5 trillion parameter model with 2,048 experts. Mistral had one in 2023 that was 47 billion parameter model with 8 experts. And DeepSeek has done this once before as well, 16 billion parameter model with 16 experts. R1 is 671 billion parameters with 256 experts, but they're activating 8 at a time. I'm getting ahead and I've sort of ruined my analogy now, but the idea though is you have these subnetworks that are specialized in specific topics, and you choose to activate a certain number of them at a time. So you go back to the decision maker analogy, and now you have a gate function or a chief of staff that sort of selects which experts to put in the room. And what this does is you're no longer paying every expert to be there for questions they don't need. If it's a question that requires a doctor and a lawyer, you're not paying a linguist and a Spanish to English translator, an accountant to be there. And so this reduces, in practical terms, this reduces the number of computations the model has to make.
Okay.
But the gating function also weights each expert that it does select. So you're also sort of getting a proportionate influence from each expert on the final outcome. So it reduces the computational cost, but in some ways it makes the answer like less noisy as well, because you're able to sort of appropriately weigh which expert should sort of have more say in the final decision.
Ilya, Rebecca, do you have anything to add to that?
I think that's very well explained. Yeah, I think, is it impressive to me? Not really. Like it's like it's a thing that we do. Like there's a lot of work divided up against like different parts of the network. But yeah, the execution is quite superb. And I think this is the world that people want to get to with agents as well, right? Where like instead of training everything on everything, you have models that specialize. I mean, to me, that's not really innovative. Like it's great. We should do that, but it's not like innovation per se. But yeah, color me skeptical.
Fair enough. Okay, let's move on to the next topic, or I should say, word of the month: distillation. So that's been used quite a bit. So Rebecca, I'd like to ask you if you could talk a little bit about what it means, how does it work, and would it be accurate to some degree to say that the DeepSeek researchers showed that they used an AI-based model to train AI?
So I know you set some ground rules at the beginning that said we weren't allowed to, talk smack. So I'm going to acknowledge that this is, I think, one of the most controversial things.
Fair.
Primarily because they did use the term distillation. And if we think about what it means to distill in sort of a layperson sense, I think the word distill does describe what they actually did. But distillation, I think for most of us, we think of like the Hinton et al. Version that came out in 2015, 2016, where they're really thinking about knowledge distillation. And the way that they did that is by basically training smaller models to match the probability distributions of the larger model. Unfortunately, knowledge distillation is expensive. So I think that I'm not actually sure how it is that the term slippage of the word distillation happened, right? This could be down to translation, right? Because we're an international community of people who are speaking across language barriers also. And so potentially that is the reason. Potentially they are essentially soft launching a new approach to distillation. Because what they actually did is, I would say they used larger models to generate a training data set, and then they used that training data set to do sort of like, not exactly supervised for fine tuning in the way that I'm used to thinking about it, but I would say like AI supervised fine tuning, which is, a way of distilling information. Does it conform to Hinton's kind of definition? No, but it's a much cheaper approach that's interesting. So I think, and maybe I'll stop there before I say anything that gets me into trouble.
Fair enough. Ilya or Steve, do you have anything to add? Ilya?
There are two problems in computer science: what to name things, and so yeah, I mean, distillation is a very broad term, and I think people throw it around. I mean, to me, like logic-based distillation versus feature-based distillation versus response-based distillation versus self-distillation, those are very different, right? And it's like you're distilling very different things. It's whether or not you're using in a feature-based distillation, you're basically using the hidden layer representation, right? And like what Rebecca described and what these guys have done, it's very different from that. And so I think we need to be a little bit more careful when we talk about distillation to kind of show what flavor we're using. Now, having said that, like I do think distillation techniques in general are amazing. They suffer from the same problems that we've already talked about with generated data. Um, but I do think they're amazing because, especially if we live in the world once again where people are open sourcing their models, then like this could accelerate the community of researchers and practitioners by a ton. But we just need to be a little bit careful with the language that we use.
Yeah, I think that's a sort of the heart of the matter is, for a community that is fundamentally a scientific one, we're often not as disciplined about our language as maybe we could or should be. And that's probably largely down to how fast how fast things move. But that being said, I think I fall on the side of this was a poorly chosen phrase or poorly chosen way to describe this. It doesn't make what they did any less interesting. In some ways, I think it maybe sort of distracts from how interesting what they did was by kind of muddying the waters and making it controversial, because the technique they used is something that has been around, is something that people use all the time. They just, by all accounts, used it very well. But again, I sort of tend to fall in the camp of distillation to me means we're modeling the probability distributions of the original model and trying to recreate that with a smaller, more efficient model. And that's sort of objectively not what they did here. And so it makes the conversation a little bit harder.
Fair.
Yeah, and back on the language, I think the term that I absolutely hate is AI, because people just throw it around. There is an actual scientific definition for AI, right? But it includes planning under uncertainty and machine learning and a bunch of other things. And so I think a true AI should be capable of training the next generation of AI, even training it to be better than, the original, because we do it, right? It's like my kids are way smarter than I was at their age. And so like clearly that's possible somehow. So I think true AI could get to the point where like that vision for distillation, where like you pass on the knowledge to the next generation of models is possible. What we have right now is statistical techniques that like approximate the average output. I personally would not call that AI.
That's fair.
I'm here to be a skeptic.
As you should be. Okay, before we open it up to audience questions, my last question is to focus on the application of these techniques. So how do you foresee them being used in industry? What does this change if you are part of a company that is looking to implement AI products or features or systems? Does this change anything for you? And I open it up to any one of you. Go ahead, Ilya.
I'll go first if you're okay with it. I mean, I think smaller models change everything for you.
Yeah.
It honestly, like when ChatGPT first came out and people were like, "Wow, transformers are a thing." I'm like, "Yeah, we've had them since 2016. Welcome to the party." But people were like, okay, like I need to run it. And I'm like, okay, so this is what it means to run it. And everybody's like, well, I don't want to give my data to everybody. And I'm like, well, yeah, but do you have a cluster of H100s? And very few people did back then, right? And so if you can run it closer to where your data are, then like these models are economically viable. Like you can start getting real value from them. So yeah, I think this changes a lot. And again, there's some credit that goes to the DeepSeek team for sure.
Yep.
But all of these optimizations are things that were being discussed and are implemented by a whole bunch of people right now. I think what they've done better than anything else is they forced the industry to like really start applying it. Same way that ChatGPT forced the industry to really start applying transformers. Google was sitting on it and being like, you know, we want to make sure we do this right. And now they don't even care. Oops, I went into the wrong place. I'm gonna stop here.
That's
No,
okay.
I think I'm gonna pick up where you're letting off, Ilya. I think that like I always so when I entered the field of data science long ago, there was this sort of maxim that came out, that I think has like basically defined really a lot of things. It's defined sort of how people do data science. It's also defined kind of the cloud economy, which is that more data beats better algorithms. That was the big takeaway from the Netflix prize, right? That if you were trying to do a recommender system to help, predict movie recommendations, that having more data about movies that people had already seen, but also like metadata about the movies was a faster path to doing better recommendations than, some really clever bespoke super fancy algorithm. And I think that really like set the tone for like has set the tone for 15 years. I think that was like back in 2008, I want to say. So maybe more than 15 years, right? We've believed that more data beats better algorithms. And I think that to piggyback off what you said, Ilya, I think that the DeepSeek paper is kind of like a shot across the bow of the cult of big data.
Mm.
Because I think that they showed that you can do a lot with less data. And I think it's just really like fascinating because we've sort of believed the opposite for a long time.
How about you, Steve, given your background in manufacturing or any of your other experiences?
Yeah, I mean, there's a couple things that come to mind, and to start maybe by picking up with what Rebecca was saying, there's this concept of marginal return, right, or marginal marginal gain.
Yep.
And I think for a very long time, there was sort of this mindset that spending a lot of money to pick up small incremental gains was the way that we were going to move forward. And in reality, that probably, as the industry matures, is going to look a little bit more like a bell curve. So better algorithms, better data. I mean, we've seen what we can accomplish with what is pretty nearly literally all of the data in the world. And we've sort of hit a bit of a ceiling with it. And so now we're learning that we can probably do more with less and I think I err on the side of this is all part of the natural learning progression, right? Like data was fueling a lot of this, and so just pushing more data through the pipe was something that it's very, I think, intuitive to have explored. But if we're sort of at the end of that at the end of that line of track, then this is sort of the next logical progression. And I think hopefully this is sort of a wake-up call that what the direction we were heading maybe wasn't super sustainable, especially when you have someone like Elon Musk saying we've exhausted all of the human generated data available for, and I think that's a bit of a over dramatic statement, but it's not like totally 100. I mean, there's some truth to the fact that these models have been trained on very nearly all of the data in the world. So where are we going to go from here? Right. But that being said, I think if you specifically asked about smaller companies, and I think there's two really huge implications for this. The number of viable use cases for hosting your own model has grown exponentially, or will grow exponentially, as these efficiencies propagate through the industry and become more widespread. And that's really exciting, right? Companies that previously wouldn't have been able to consider hosting their own model or sort of getting into the AI game in a useful way, the viable opportunities for them to leverage this technology are going to grow significantly. The other thing that's really interesting is this could potentially sort of release some of the demand pressure on the higher end GPUs. So if these models become more efficient, Meta currently owns something like 350,000 H100s. And if they now only need 175,000 H100s to do what Meta does, then this hardware might also become more widely available. There's no shortage of interesting problems and meaningful problems that can be tackled with this technology. So seeing sort of access to the best hardware for tackling it become a possible reality for more groups is a really interesting side effect of this as well. I'm still relatively bullish on NVIDIA, even though their stock has taken a beating. I suspect that being sort of the best company in the world at making making the GPUs that everyone still at least currently wants. I'm sorry, that probably sort of pushed things a little into the
no,
side.
that's fair.
But my hope is that for every GPU that Meta no longer needs because they're going to implement these optimizations, 100-person company or 500-person company or a 50-person company could pick up that hardware and do something really cool with it.
Interesting. So smaller models, better algorithms, less data, more opportunity. Well, we are about up on time. So with that, I would like each of you to just offer your final thoughts. Before we do that, thank you, Rebecca. Thank you, Ilya. Thank you, Steve, for taking time to read through the papers, to do the work, and to share your expertise with us today. And I'm putting your contact information up there. If anybody wants to reach out for any reason, please do so. So with that, final thoughts before we sign off. Who would like to go first?
I can go first. I'm going to veer into the category that you told us not to veer into, but just very slightly. And the thing that the thing that I keep thinking of is how does this change societally, right? Like, what does a model like this mean societally? And one of the things is that it's going to be open source. And Ilya Sutskever at NeurIPS said a thing that like we were all thinking, but he put it better. I don't remember the exact phrasing, but he said basically, as the models get more intelligent, they're going to be harder and harder to evaluate. And if you combine that with an open source model that everybody can run it, but nobody can know how good it is and when it glitches. And, it doesn't even take harmful actors in order to cause a lot of harm. So that's one side of it. The other side of it is if we're truly moving away from the paradigm that we're just trying to throw more data at it, then there's not as much incentive for companies to, I need to be careful, Meta is a former employer, borrow your data to enrich themselves. And so perhaps this is a really good thing for privacy. Perhaps the fact that you don't have to have every last bit of data from everybody does mean that like the privacy aspect is going to get considerably better than the world that we used to live in. And so both of those risks are real, right? Like clearly in a world where information can spread quite quickly, both malicious and non-malicious harmful generations of it could have tremendous impact. But it would be nice to see what the world with some privacy is for a change. My generation has not seen that, so it would be cool.
That would be a fantastic outcome. How about you, Steve? Any final thoughts?
Yeah, this is probably not the opportune time to bring up something completely new, but one thing we didn't really touch on was the environmental impact of this. And it's interesting. Obviously, less computation means less energy spent. So that's really, really cool. But my other thought is that this might be the equivalent of having the, having the carbon output of cars and then doubling the number of cars on the road. Because if my hope that this puts the technology in the hands of more people comes to fruition, then maybe the net impact is not going to be as significant as we think.
Right.
So, but to me, I guess that just emphasizes like we still need to work on the environmental sustainability side of this, and that computational improvements aren't necessarily going to be what solves that problem.
Absolutely. It's a good takeaway. And final word, Rebecca.
I guess I would say, I said that I didn't think that DeepSeek had proven that you can kind of wholly generate synthetic data without people involved.
Mm-hmm.
But I guess what I would say is, imagine a future where that is possible, where it's sort of trivial to generate synthetic data. In that future, the differentiator is your specific domain data, right? So your primary data sources at your organization, or maybe your individual data as just a person.
Right.
That is the differentiator.
Great. Well, thank you again to each of you for sharing your expertise today. Very much appreciate it. And no doubt this is not the end of the story. There'll be more developments, more optimizations. Hopefully we'll be back talking about them in a few months. And until then, again, thank you. And I hope all of you have a great weekend. Take care.